Okay, Igor, we'll continue now.
Okay. Happy to see you again. So I'll continue with this topics of doing combinatorics of stranded graphs, because if there is one new thing in these lectures that you haven't seen before, it's this funny combinatorics that you get out of models from tensors with more than 2 indices. So I reviewed planar diagrams last time. Those of you who have not seen them saw that in matrix models you basically have at most a factor of n squared out of a connected graph if it's planar. Okay, so let me come back to this d equals 0 model. So to strip away all the dynamics and momentum integral, sometimes it's convenient to just go to d equals 0, right? So the model that I was starting to discuss was just an integral over n cube real variables, right? So each of these phi ABC is a real variable, and you integrate from minus infinity to plus infinity. And then you have the Gaussian weight, phi ABC squared for each one, and then you have a certain interaction, which is written like this. Now, a short quiz. Out of these two diagrams, which one corresponds to this interaction? It's okay. Maybe it's too difficult for. But remember, okay, just looking at this, another quiz. Which one of these is tetrahedron and which one is pillow? What I called yesterday. Yeah, so left is tetrahedron and right is pillow. And the property of tetrahedron is that every 2 vertices are connected by just a single line, right? While here you have, for example, this phi connected by 2 lines to this one, right? So this is a different topology. This one is planar, and this is inherently non-planar, right? And if you look at this interaction, as I stressed last time, to get the simplest melonic limit, it's important to take the tetrahedral interaction. So if you look at this one, every pair of fields has one index in common, so it corresponds to this one. So this is the tetrahedron, and this is the pillow vertex. And both of them are, of course, respecting the ON cube symmetry of this model. So this is the d equals 0 ON cube symmetric model. And then you can basically start doing, so you can just think of it as a particular kind of 5-4 theory, right? Where you just have a triple valued index. So you can rewrite this interaction, the quartic interaction, in terms of some j with 4 composite indices and fields phi, right? And this j can be written explicitly in terms of delta functions. It's basically a product of delta functions. So this would be an exercise is to write this explicitly, right? It's no big deal. You basically just lay out, you write the interaction as, say...
Is it clear that it is even positive defined?
Yeah, that's, so it's formal. As I stressed last time, this particular interaction is not positive. So that's actually a factor in all this business. But my excuse for this was that even in these double-scaled matrix models, we had to drive ourselves to the regime. Yeah. No, actually, this is what I said last time, that for n bigger than 1, actually, there are negative directions. So this is not positive definite. Not positive in general.
Sorry, a question. Is there anything wrong with just doing fermions instead?
Oh, you're jumping way ahead. I'm just doing... Yeah, the end result will be that I'll replace these by Majorana fermions, and then yeah, since you asked, I cannot do Fermi. The zeroth order idea is let's replace phi ABC by a real fermion, right? By psi ABC. Then you have a bit of a problem in d equals 0, right? Because psi ABC, like psi 1, 1, 1 squared is equal to 1/2. So,
Psi dot, I
yeah. When did you arrive? Okay. All right. So anyways, but I'm just doing the scalar field stuff, and then I'll come back to. I'll actually not completely waste the scalar field discussion because you can then promote this to just d-dimensional, say, Euclidean field theory, and again hope that at large n you can still do business. Right. So yeah. So there is no d equals 0 model, but later we'll get to a very simple d equal 1 model where these are just real fermion degrees of freedom. Okay, and so I was saying that, yeah, this is a good exercise for students, is simply to rewrite this interaction in terms of, you can basically write some phi A1, B1, C1, phi A2, B2, C2, phi A3, B3, C3, 4B4, C4. And then write some J interaction tensor A1, B1, C1, dot A4, B4, C4, in such a way that this equals this, right? And obviously, this is just a bunch of delta functions that perform contractions here. So this is a good exercise for students. And then you can then it becomes pretty algorithmic, like how you evaluate diagrams. There is sort of the pictorial way of doing them, and then there is a complete brute force way of doing them, which is just writing diagrams and contracting these delta functions together. And of course, the propagator phi ABC with phi A prime, B prime, C prime. This is just delta AA prime, delta BB prime, delta CC prime. So for example, you draw this diagram. This is the first diagram that you encounter, right? It's a double. You can call it a double bubble or a snail. It's basically a snail with two legs tied together. And so this is the first diagram of order G, right? And then the next diagram, it comes at order G squared, right? And this is so this is a bubble type or snail type diagram. This is the first vacuum melon diagram. And then at order, so this is G, right? This is G squared. And the other G squared diagram is again of bubble type. Right? It's again a bubble type. And then you can basically go ahead and just derive without particular difficulty, derive what the contribution of these diagrams is for log z. So if you're computing log z divided by n cubed, right? It's given by the sum of these connected diagrams, and here you get minus 1/8 gn. Here you get 1/288 times g squared times n cubed plus 3n plus 2. So you see that there are these subleading pieces already appearing, but the first term is n cubed. And this one gives 1/16 n squared times g squared. And then you go to like order g cubed and higher. But this basically shows that this explicit evaluation shows that what I claimed last time, that that the snail type diagram is suppressed compared to this bubble type diagram if I take this scaling limit where g is of order is lambda divided by n to the 3/2, right? So then you see that this diagram will become like lambda over root n, right? This just goes like lambda squared, and this one goes like lambda squared over n, right? Right, lambda squared over n. These are just the leading pieces. Then there are also sub-leading pieces. Okay, and then there is, but it's useful to also reproduce these in a pictorial fashion. So I wanted to try to show how you sketch some of these things. Yeah, if there is one thing you learn from this class is how to do this double line and triple line notation. So let me do the following then. Let's take just the leading bubble diagram. Okay, so this, and try to draw it. And so you lay out this vertex, right? The vertex looks like this. And suppose there is just a single vertex. Right, and then you want to, so the unstranded notation is just this object here, okay? And let's first do this in the matrix model. In the matrix model, the vertex looks like just this planar vertex, and then you contract, you basically connect this line and this line like this, right, and this one and this one. Right, so this shows to us clearly that, so let's count the powers of n in the matrix model, right? Remember, in the matrix model, the limit was that G matrix was equal to lambda matrix divided by n, right? And then you were supposed to always get n squared out of planar diagrams. Right, so here you get 3 index loops, right? One outer one and 2 inner ones. So you get gm times n cubed, and this is indeed n squared times lambda m. So this is the first kind of sanity check that you're doing the right thing. And then the whole art is to add this this middle line, right? So the middle line has to be added in this tetrahedral way. So let's. So how do you do it? You basically want to draw it in so that one temptation is to just draw it like this, right? But that would not be tetrahedral because in this vertex, this blue line has to cross itself in a non-planar way. So basically, what you need to do, therefore, is to do the following thing: when you go through the middle line, it has to go under itself, right? So the blue line adds only one index loop, right? So therefore, in the tensor, model, what you will get is you just get g times n to the 4, right? And this is equal to n cubed times lambda divided by square root n. Okay. So this is basically, you see that this is suppressed, but it's suppressed rather weakly, just by square root of n, right? Very weak suppression. I should, jumping ahead a little bit, since fermions were brought up, thanks to Daniel, is that if you go to the matrix quantum mechanics, in the simplest version of it, this diagram simply vanishes because the propagator at coincident points is 0. So while in scalar models you can even get these 1 over root n interactions, like there are different theories where this vanishes. In higher dimensional field theories, the tadpoles just vanish after you do analytic continuation, right? In fermionic theories, they also vanish. So these 1 over root n corrections are not entirely generic, but basically, nevertheless, they can be present. And this is a stupendously large correction, right? So, for example, if you think about the equivalent bosonic SYK-like model, then, like in Subir-Stock, he used n, and I will call it n SYK. That's really n cubed, right? So this correction would give us n SYK to the power minus 1/6, right? This is certainly not something that's widely discussed in SYK context, and it's not, for example, present in the Schwarzian action. Okay, so now what about so this graph is somewhat suppressed, and then as I showed last time, I already drew this, but maybe I should draw this again. If you, what does the leading melon look like, right? Again, it helps to basically start with the matrix model graph. Right, so this is a graph of order g squared. So let me just draw the same two vertices, and now there will be two. Okay, and here another one. I think. Maybe I'll just leave this as an exercise. Yeah, you let's see. You basically want to convert this graph to. Suddenly, I'm forgetting if. No, I think I should draw it like this. So one of them will go like this, I think. Okay, so this will connect to here. Yeah, the outer one. I think this one has to go. And this one goes like this. Okay, and then this is connected in this fashion. Right, so this is the graph that we get in the matrix model, right? Everyone agree? And then let's count the loops, right? So there is one outer one. Let's see, 1, 2, 3, 4. So this, I think, works correctly, right? Because we have, so in the matrix model, we will have G matrix times n to the 4. And this is indeed n squared times lambda matrix squared. GM squared. Yeah, GM squared. Let's see, 4 loops. Right, and then again, the whole art is adding this middle loop consistent with a tetrahedral interaction. Okay, and that is not hard to see that there are basically two loops that you can create. One will go through like this. One will go through like this, and the other one will go intersect it under it, go under it here. Makes sense, right? So in this case, unlike in that case, we actually added two blue loops, right? And then you get, so in the tensor, you get basically g squared times n to the 6. And this is exactly n cubed times lambda squared. Exactly as what we got through the boring way of calculating it. But I think it's pretty fun to do this and play with these things. Okay. And then you can do the last one and stuff like this. But now, where is the gist of this story? Okay. So you can actually prove, so what we saw is that from these first 3 connected graphs, you cannot exceed the n cube scaling. And the only, namely if you take log z over n cube, you'll get something either finite or suppressed, right? If you take this special limit. So can we prove it? Okay. Can we prove it? And here comes the proof, or at least an argument. This is in these TESC nodes that you can easily access. Wait, no, they're on HepTH and yeah, and they were part of the suggested reading. Okay. So actually, the way we constructed these stranded diagrams was by first drawing the double line matrix model graph and then judiciously adding the third line. But the way you prove, okay, okay, so try to prove that prove melonic dominance or dominance. Namely, the first part is that no graph. So when we scale, so first of all, assume this pure tetrahedral interaction. Pure tetrahedral model. Okay, and then take scaling that g is lambda divided by n to the 3/2. And then you can prove that no graph, or you're just generating graphs of 5-4 theory, even with or without tadpoles, things like that. And so prove that n cube is the maximal scaling of f. And n cube, of course, makes sense. This is also the total number of degrees of freedom. Okay, so this proof is actually surprisingly simple for this business, and it goes as follows. You can first erase. So when you lay out this stranded graph, for example, this one, you can imagine first erasing all blue loops, and you're left with red-green graph. And this red-green graph is just the type of fat graph, with double line graph that we see in matrix models, right? Then you can also imagine erasing all red lines, and then you see the double line graph like in blue-green one, and then there is the third one. Okay, so basically we can forget, so you erase all loops of a given color. For example, erase all red colored loops, and then you can then calculate. So find FBG, which is the total number of loops in the remaining graph, which is just FB plus FG, right? So how is this done? You basically use this Euler identity in terms of the Euler characteristic. So this remaining graph will just be the Hoff type graph. So we write that FBG is equal to chi BG plus the number of edges in this BG graph minus the number of vertices. Right, but then you also have, from the topology of the graph, you also have the constraint, like if you go around each vertex and mark all propagators, you'll see that each propagator will be marked twice, right? So you also have that the relation that EBG is equal to 2 times V. 2 times V. So therefore, this becomes FBG is equal to chi BG plus V. Chi BG plus V. Right? And then you can apply this also to BR and RG. Right? So similarly, you have like phi BR is equal to chi BR plus V. And the third one. Right? Okay, so then let's add them all up, right? So we see that FBR, so FBG plus FBR plus FRG, which is incidentally equal to twice FB plus FR plus FG, right? And this is equal to chi BG plus chi BR plus chi RG plus 3V, 3 times V. So then divide this by 2, right? And you get
I'm sorry.
yes.
Can you remind please what is F?
F is just the total number of loops in the BG graph. Like, for example, if you erase all red loops, you can just count here, right? Like you erase the red loops here, you're left with, let's see, 2 green loops and 2 blue loops. So there will be 4. Yeah. So FBG, yeah, here, for example, FBG is equal to 4, and FB is equal to 2, FG is equal to 2. Now, maybe someone can tell me, why am I counting this? What does each index loop give me? Factor of n, right? That's exactly, so in the end, the scaling of the graph will be basically, the scaling will be n to the power FB plus FR plus FG. Each loop gives me a factor of n times g to the v. Right? This is the contribution of the graph. Right? And here comes this amazing fact that, so divide this by 2, right? So you divide this by 2 and you get that this F total is equal to 3V over 2 plus this chi plus chi plus chi, BG plus BR plus GR divided by 2. But then the whole point is that this chi is actually bounded, right? We have the relation that chi is bounded by genus, right? It cannot be too positive, right? So for a connected graph, what we have is that chi is equal to chi is equal to 2 minus 2g, right? Right. So or chi over 2 is equal to 1 minus g, right? So this therefore gives me like 3v over 2 plus 3 minus genus of BG graph minus genus of BR graph minus genus of RG graph. And genus, of course, is either 0 or positive, right? So then you reach this immediate conclusion that the maximum scaling, therefore, is n cubed. So the maximum scaling you can achieve is n to the power 3 plus 3v over 2, right, times g to the v. And this is exactly n cubed times lambda to the power v. Yes?
Where did you use the tetrahedron?
Very good question. So where do you think? I was actually going to exactly ask this question 30 seconds later. So far, so let me just first finish this argument. And so clearly you see that because genus can be either 0 or positive, right? Then for this argument, you see that this is the maximum scaling. And the graphs that dominate are the ones where each sort of subgraph, double-line subgraph, is a genus 0 graph. Okay? But then let me just go back 1 second. And even when you go back to this minimal snail graph, did I erase it? Or maybe I did erase it. But for example, if I go back, if I use this one, and let me just try to make the simplest graph out of it, right? So what can I do with this graph? I can just connect red with red. Right, and blue with blue, and green with green. And and here the green. So, yeah. Okay, let's just count how many powers of n we have, right? So now suddenly, so this vertex we will call like G pillow, for example. So this is a very different topology of a vertex. Is this pillow vertex, right? And the number of loops is 1 green and then 4 of these. So you get GP n to the 5, right?
Isn't another graph where you couple the G's, the green's the other way, and you get then gives you n to the 6.
No, there is no way to get it. No, this is, I'm supposed to think of this as a single line coming out, right? So I can only connect it like this.
But if you're connected that way.
No, I'm not allowed to do that, okay. I think. Yeah, you just think of this as a single white. I'm basically drawing this type of graph, right? And just replacing this by these 3 strands. Yeah, I think this is the maximum I can get. But clearly this n to the 5 is bigger than what I obtained for this one. So the fallacy with this vertex is that when I erase the green line, the graph becomes totally disconnected. Okay? It looks like this one and this one. So you get a disconnected graph. So the special thing about the tetrahedron is that each subgraph will look exactly like a single traced Hopf graph. And only in that case can we apply this chi identity. Otherwise, we get like a double trace theory, and then chi can actually, it's effectively like getting negative genus or something like that. And you see it, you run into it right away. So the argument, as you pointed out, very crucially relies on this special tetrahedral vertex and would not fly through this one. Here you have to work harder. It's still okay to get this type of theory, but then first of all you need to scale GP faster to 0. You have to put lambda p divided by n squared, and then this will still go like n cubed times lambda p. But in this type of scaled theory, actually snails are not suppressed. They dress everything up, and you have to deal with that. But But the experts on this business know this stuff, and so you can still get like a good theory this way, including snails. But the simplest proof that I showed relies on purely tetrahedral interaction. And yes.
And the 3 plus the 3V over 2.
Yeah.
The 3V over 2.
Yeah, 3V over 2 goes together with G, right? Yeah, this 3V over 2 just comes from here. Like 3 came from the chi's, right? So it's exactly the 3 you need, because you want to see that this graph goes like n cubed times something that's kept fixed, like, right? It's G n to the 3 halves V. Right, this is n cubed times G n to the 3 halves all to the power V. Okay. So I basically showed that with this tetrahedral vertex, nothing is going to beat this graph. But then there's still a somewhat more complicated step, which is to show that only the graphs that we call melons are the ones contributing at this n cube level. And I think you can read about it in the notes. Essentially, it relies on the fact that all the vacuum melonic graphs essentially have the following structure. They basically look like this, that this is the fully dressed propagator and this is another fully dressed propagator. Okay, so the set of, so these are all melonic graphs. To start drawing them in stranded notation after a while becomes a full-time job. Like, I mean, even this you take. But I just want to sketch a few more. So just to remind you, basically we have to iterate this. So you're iterating. For each propagator, you can insert inside it this melon or sunset. And then the vacuum graphs you get, so in addition to, so this is the leading connected one at leading order, and so this is the only one at order G squared, looks like this. Then at order G to the 4, you have, for example, this one, where you have this and this. This is, you can also see them at the beginning of these lecture notes. Right. And then the next one can be drawn like this. There are various ways to draw them, and then you can have, so this is at order G to the 4, to order G to the 6. I think there are only two at order G to the 6. There is another one which is just like this. So this is also G to the 6 and so on. Okay, and actually a very prominent class of graphs are these ladders. Like when you sort of look at this one and start inserting more of these, right? And this is how you basically solve the Schwinger-Dyson equation, by sort of putting in more and more of these. And they look a bit like melons within melons. Like once you have, for example, this one, you can just draw it sort of like this. And this is and ad infinitum. And these are these ladder-like things. So the point is that, I mean, you see that all of these graphs are planar, but there are a lot fewer of these graphs than there are of planar graphs, right? But it looks like a consistent set of graphs which is picked out by this rather peculiar large n limit with the specially chosen tetrahedron interaction.
Igor?
Yes?
But what physical properties can you compute using this leading order graphs? What is it that you...
Well, so people always were hoping that just like 2D quantum gravity coming out of matrix models, that say 3D quantum gravity is going to come out from these ones. And that's where the tetrahedral comes in crucially, because this is really a tetrahedral shape, right? Then you start gluing them at the vertices, and then you build up this 3 geometry. That was like the original papers were like Ambjorn and collaborators had this rough idea, and Mark Gross and I forget the Japanese. Yeah, I'll remember his name, but it's all referenced here. And this was around 92. But people got completely bogged down in analyzing the large N limit. First of all, they took a model which was like the hardest one. They basically took a single symmetry group, like a single ON, and took a field which is like symmetric 3 tensor of ON. That's one of the hardest to analyze. Like one of the tricks here is to take completely non-symmetric tensor, like phi ABC with ON, ON, ON group. Then the proof becomes rather straightforward through this coloring technique. But then it turns out, actually, and this Tarnopolsky and I wrote a paper on this, that if you take just a single ON and take a traceless symmetric tensor, that's also melonic. And we did it by computing to pretty high order, and then people proved it. But it's much, much harder to prove. It's some combinatorial proof. So that's sort of one motivation. But this 3D quantum gravity. But I think this sort of branched polymer-like structure of these graphs is what puts a big, big question mark on that philosophy. And more precisely speaking, when you solve this log z as a function of lambda, you do see the branched polymer scaling exponent. This is what I mentioned last time. Namely, you see that when you solve this model, you find that there is some that f over n cubed has the leading critical behavior, which is some lambda critical squared minus lambda squared to the 3 halves. And this corresponds to this susceptibility exponent gamma, which is equal to plus 1/2. And this is the most generic behavior in these sort of random systems, this so-called branched polymer. Yeah, this string susceptibility is basically always defined as some delta, like f scales as delta to the power 2 minus gamma. The crucial thing for the pure gravity, for the pure random triangulation model, was that gamma was minus 1/2, and that agreed with Liouville theory and all that. But here you get this undesirable phase and stuff. But I think the true physical motivation after a couple years ago is these SYK-like models, because as Subir showed in his first lecture, essentially the same diagrams pop out from this model where you treat J as random. Oops, did I erase that? Maybe I erased that. But so he took the model where there is some random coupling, Gaussian distributed, and you start doing averaging over J, and you again get melon dominant. So these are two different representatives of this class of melonic theories, where only the subgraph shows up, subgraphs show up. This is still somewhat mysterious, and I'll say more words about it. Just at the level of graphs, it just pops out. Like, I think it's in some ways rather surprising that this peculiar tetrahedron interaction filters out only these graphs. I think I showed how this works, but this is in some sense the biggest news here. And then you can start studying the models in a bit more more dynamical detail. And the model that I'll focus on will basically be this fermionic model in D equal 1, which has apparently the same Schwinger-Dyson equations as the SYK model. And there is like a Majorana version, there is a complex version, there are different versions of these models. So there seems to be like this sort of, so far it appears that every random model has a non-random tensor counterpart, and you can build these sort of counterparts, but which are the same in the leading large n limit. But when you go to the sub-leading limit, then it looks very different, very, very different. And so just to finish with sketching these plots, I prepared this. This was a little too laborious to draw. But for example, let's look at this graph. So in the matrix model, this is actually the first representative of an important class of graphs contributing to 1/n correction. You see, there are no self-contractions, so it's not a snail-type graph, it's just a particular type of graph that appears in 5-4 theory. So this is the matrix model story. If you count the loops, you basically see 1, 2, 3, 4, and 2 green ones, right? So you get gm to the 4, n to the 6, right, which is indeed n squared times lambda matrix to the 4. Scales exactly how you would expect the planar graph to scale. And then let's try to fill in the middle line, okay? And then just by inspection, you can basically see that you can, for example, put a blue loop through this cycle here. So you put it through here, and then this one can just go through in the tetrahedral way and everywhere sort of go under at each of these vertices. Right. So you see that you've added 2 blue loops. So therefore in tensor model you get G. So in tensor you get G to the 4 times n to the 8, and this is basically n cubed, which we always take out, right, times lambda to the 4, and then 1/n. So this is really suppressed by 1/n, and there's no excuse to ever drop this graph, right? It's there, for example, in fermionic theory, it's there in all theories. And in fact, there is like a whole class of additional graphs that have the same scaling. Like the same scaling is achieved where you start putting some ladder here. They all contribute to 1/n. And some people call them, I don't know, sandwich graphs or something. You can think of this as the bread or the bun and some generous heaping of corned beef in between. Right, so this is one of the classes of graphs that contribute at 1/n. And you see that this is definitely 1/n, so this is like 1/nsyk to the power 1/3. If you read Witten's historic paper, he actually wrote 1/nsyk to the 2/3, but I think he wasn't thinking too hard about this. He probably wrote this paper in one day. But he made this important point that the scaling is a fractional power of the kind that you will never get in the Schwartzian action and things like that. And this is something that I'm in particular thinking about now, which is the origin of these fractional power corrections, for example.
It's worse than Schwartzian. It's sort of any master field.
Yeah, right.
Anyway, regarding this larger limit as some kind of classical theory where n cubed is Planck's constant.
Yeah, I think the answer is that this theory actually has a vast number of additional operators, which, well, we discussed this, and I'll also mention this a bit later on. And it's due to the fact that these these sort of tensor models have a factorial growth of the number of higher particle operators, unseen in string theory. In string theory, you get it most exponential, and here you get a faster growth, and I think the two effects are related. So the two things are rather different in terms of the 1/n corrections. Okay, so now
It really means that this is, unlike SYK, not it's not large in theory in the sense of expansion around the classical.
yeah, perhaps. I actually think that there is some kind of operator mixing between SYK-like operators and other operators that can give some. Anyways, it's a bit half-baked, but
Somehow that seems like a general feature of this kind of things with the disorder versus not the disorder, right? Like Stephen Douglas and Phil Stott have this whole story. It only works after you average the disorder. These nice. Then maybe this picture with the
No,
wheel
it's only
shape.
happening. Sure. Yeah,
But you have to have this. Somehow you need the disorder averaging to make it classical.
right. But here you're just sort of looking, following your nose and going sort of one step beyond matrix model. And okay, so let me then move on to the more of a physics. So far it's been like a bit like doodling with colored chalk, and it doesn't seem like very physical, right? But so as Witten pointed out in his paper a little over 2 years ago, there is this connection with the SYK model. And he wrote down some model with 4 rank 3 tensors. Then Tarnopolsky and I simplified it to 1 rank 3 tensor, which is very similar to just the fermionic version of this minimal O-cube model. I already talked about how you might work it. So basically the action of this model then will be so the Majorana models, then you don't worry about this instability. You just say here is S is integral dt, right, times I over 2 psi ABC d by dt psi ABC. And then here you add like minus g over 4. Let me just write it here, minus g over 4. Psi 1 b1 c1, psi a1 b2 c2, psi a2 b1 c2, psi a2 b2 c1, right? So that's so now we're not worried about positivity. In fact, so the Hamiltonian, and usually it will be convenient to add a constant here plus some constant, just to make sure that the energy spectrum is symmetric around 0. Then it with some specially chosen constant. And then, so what do you have? Then you just have a Majorana quantum mechanics. You can think of it as a bunch of qubits, just like SYK model. So you have the following anti-commutation relations, right, which is just a bunch of delta functions, dB prime delta cc prime, and then the Hamiltonian is just g over 4 times this thing, you know, this psi, exactly what I wrote here, and then there is some n to the 4 over 4. Right, and this is a purely tetrahedral coupling. Tetrahedral. Now, this fermionic model has some additional nice features compared to what I said before. So, and these nice features did some presence of additional nice symmetries and simplifications. So one feature is that it obviously has a SON cross SON cross SON symmetry, but it's realized in the following way. So if you write down, for example, the SON charge, like for example, there is SON, the first SON charge. This is just a commutator. It's Q1 A prime, which is I over 2, commutator psi ABC, psi A prime BC. Okay, and then there is completely analogous like Q2 BB prime and Q3 CC prime, right? Completely analogous, right? And now, if you look at these pillow, so as I alluded, there are 3 possible quartic pillow operators that you can write down, right? This, I said this last time, but so for example, you can so the tetrahedral operator we can write like this, right? We always have this. Right, and here is. So this is the structure of the tetrahedral coupling, but then the reason these are called pillows is something like this. You basically have like this one. Oops. And then the 2 red connections here, and then the other one. So this is a general operator that was also present in the scalar theory, right? So this is the pillow and this is the tetrahedron. But then you notice that this pillow is just the square of this charge, right? So this operator here is nothing but Q1 A prime squared. So this is just the quadratic Casimir of the group. So adding these operators basically just shifts different representations of SON relative to each other. So they're sort of non-dynamical, and moreover, you can just gauge this model. Like, so if you gauging this SON cube symmetry, just restricts to states. Which satisfy this Q1 A prime, psi is equal to 0, and same for Q2 and Q3. Then these pillow operators just vanish, right? They don't do absolutely anything to invariant states. Okay, so this is one interesting thing, and then so in some sense, then this tetrahedral Hamiltonian is the unique dynamical quartic Hamiltonian you can write, which is consistent with.
Gauging it doesn't change the leading margin limit.
Right. Because gauging like imposes order n squared constraints, and there are order n cube. In fact, it's possible to calculate the number of invariant states, and so the total number of states, of course, in this model, so n total, right, is 2 to the n cube over 2, right? Just there are n cube Majorana species, and it's 2 to the, right? And then you can start, but then the spectrum is rather the finite time spectrum is rather dramatically different from what you see in the SYK model, right? Because the first thing you see is lots of degeneracies, right? Just related to in the ungauged model, you just see multiplicities of representations of this SON. So
is it necessary to gauge the whole ON to the cube, or you can each factor separately gauge?
you can gauge some of it, but yeah, I mean, but in some sense, the dynamics breaks up into separate sectors. Like the dynamics will only act within each sector, right? So I tend to prefer to look at least at these SON cube invariant states. And it so happens that the ground state is a singlet, is SON. So this has not been fully proved, but I recently wrote a paper with Kirill Pokrovsky, who is a specialist on numerical diagonalizations, a condensed matter physicist, and Popov and Tarnopolsky. And we basically managed to determine the complete spectrum of singlet states for n. So for example, this has been fully solved numerically up to n equal 4. But n equal 4 model is already like incredibly hard to do by brute force, right? Because you have to basically, you have 2 to the 32 states, which is over 4 billion. Hard. But there is a big simplification from the fact that you can start separating states according to representation. And for example, if you add Casimirs with some large coefficients, they will push all the non-singlet states higher in energy. And then you can just, using Lanza's algorithm, determine all the remaining spectrum. And that's basically what we did. And at first, some of us were pessimistic whether it can work. But it turns out that here we found the complete spectrum, spectrum of singlet states, and there are only 36 here. Only 36, not enough to really do business with from Subir's point of view. Now, if you go to n equals 6, this number jumps to 600 million. So it's not exactly a smooth passage to large n limit. It's something like 595 million. These are just the singlet states. Yeah, yeah. So and this we can do analytically. There is an analytic computation you can do. There is even a precise number I can quote, but it's in the notes. So there are only 36 here, and their spectrum looks rather gappy. Like there is some. It doesn't look like one of these beautiful SOK-like distributions. And but then for n equal 6, you suddenly have about 595 times 10 to the 6 singlets. And this is just a part of manifestation of this phenomenon that this n cubed beats n squared. So in general, in each sector, it's going to go for large n like 2 to the, I think the number of singlets is something like this, minus n squared log n plus some corrections. And here there is some a here. So obviously at large n, this is going to be very subleading. This is the effect of gauging, kind of. This is subleading to this. And you will get huge numbers of states in each sector. And we can see it very clearly. Unfortunately, this is not likely to be, certainly you can't get it by any kind of exact diagonalization. Here we had an exact diagonalization and
Igor, the simplest singlet is just a composite of n of the elemental fields?
no, it's very hard to determine what this ground state is. It's a state of, like you have basically 32 qubits. And the Hamiltonian acts in a very complicated non-local way on these qubits. In the qubit basis, it's a superposition of also millions of states. So we haven't succeeded in writing down its wave function analytically in any kind of simple way, but we did succeed in deriving its energy analytically.
So how does it look, the spectrum?
I have it, and since I don't want to break out the laptop, I'll show the actual picture of the spectrum next time. or you can look up our paper. It's one of our best paper. It's talks about SO4 cube, but I'll certainly. I was planning to actually do some slides in the last lecture just to give more of an overview, but the spectrum looks. So one of the really good things is that this gauging removes. So the claim is that this model is like the closest tensor model you can get to SYK, to Majorana SYK. And the Majorana SYK model, not the complex SYK that Subir was discussing, just has the following Hamiltonian, right? It's basically sum of I less than J less than K less than L, right? J, sorry, I have too many J's. Let me call this A, I, J, K, L, right? Psi I, psi J, psi K, psi L. And this is a random, and here there is 1 over n SYK to the 3/2, right? And this is this Gaussian random variables with variance of order 1. And then you get this spectrum which looks, this Subir discussed last time, you get this nice distribution, sort of it looks like this, very symmetric looking. Let me try to draw this again. The interesting thing is that the model is self-averaging. Namely, if you go to pretty large n, just pick one set of A's, and you already get a very, very nice looking spectrum. So you get like this type of density. And the gaps here are exponentially small, right? Like so not only there is a peak near zero energy, and you get these exponentially small gaps.
What you said now is a phenomenological statement, or there is a proof?
Oh, this for SYK, there is a proof.
Self-averaging.
I think there is a proof. Yeah, even, I think, for these models, you can even rigorously prove things. I can't tell you who did it, but...
Well, you have to introduce replicas, and you have to look at replica of that and and go down by factors. So it's self-evident.
Right. So, but the impressive thing is that here there is actually no exact degeneracies. The ground state is not degenerate. There is just states exponentially close to it, right? But there is a non-degenerate ground state.
Well, I mean, you don't expect exponential degeneracy in your model, in that model either, right? They call it tensor model.
Yeah. So if I go to the singlet sector, like if I just look at the whole spectrum, the first thing you see are enormous degeneracies.
That's the SON cube. It's singlet sector.
Yeah.
There is no degeneracy.
There are only small degeneracies due to residual discrete symmetry. And these so the spectrum that we see in this ON, say O4 cube model, we get like this. First of all, there is exact symmetry, exact E2 minus E symmetry. And this just has to do with the fact that you can send psi ABC to psi BAC. So if you just permute there are 3 gauge groups. If they're equal to each other, you can permute the 2 gauge groups and you get all energies just flip side. Also, there are some exactly equal 0 states. There are actually 8 of them. And the equal 0 stuff is sort of special. It's like, but then you just basically have like a unique ground state here, then it's mirror ground state, then like a couple states here, another state, like, so it looks completely mirror symmetric. And So this is so far what we see from this numerical diagonalization. The ground state, you can prove a bound on the ground state energy. You can prove that it scales exactly the right way in the Milonic fashion. Namely, you can prove that that E naught, absolute value E naught, is bounded by some number which is n cubed times this g n to the 3 halves. That we did in one of our papers. So everything is basically of order 1 after you divide by n cubed. And you're piling this exponentially large number of states here. Like there is, so it's very likely that states are going to accumulate, and the argument for is that there is still Milonic dominance. So when you compute the ground state, the low temperature entropy, you're summing exactly the same diagrams as you did in the SYK model. So therefore, I can just dream of what will happen for n equals 6. And for n equals 6, it's going to look like this, hopefully.
Igor, do you have a sense of, if you look at correlation functions, how whether the transition happens more smoothly? Like,
Oh, as a function of n?
yeah, I would guess probably it's, but you don't have this funny thing where it,
I mean, maybe you do, I don't know.
Yeah, well, obviously the two models differ a lot at small n. That you can.
but how small,
yeah.
how small is
Well, that here, so in the tensor model, you can see this incredibly fast transition to large n limit that happens between 4 and 6, I would say. Yeah, for 4 there is just accidental cancellation. Like the gauging in that case actually did remove a lot of states. Okay, and then I wanted to discuss a little bit like that.
If you look at the spectrum, let's say, what you expect around 6, is it the spectrum of the theory which looks like it has a dual? Does it obey the large gaps?
Oh, no way. No, I mean, it will not have a weakly curve dual at all, right? But moreover, but this,
SYK doesn't have the large gap either.
yeah, SYK, yeah, the similarity with SYK, and this I'll explain more, is that the spectrum of bilinear operators includes this special h equal 2 mode. Like the so if you compute in this model, in the large n limit, the spectrum of operators like psi ABC, dt to the 2n plus 1, psi ABC. Like these are the bilinear operators, right? The spectrum is exactly same as in SYK, same as the analogous operators as in Majorana SYK. Namely, in Majorana SYK, people studied this psi I dt to the 2n plus 1 psi I. And the scaling dimension of psi itself is also exactly the same, because again, you're computing the propagator from the same diagrams. But at the level of numerical work, you see that there is so far like...
So there is a contribution to the density of states from the Schwartzian.
Well, even the question of the effective action, whether this G sigma effective action has not been fully clarified in this tensor model, I would say, because there are
But you do have
more
h
diff-
equals 2 moles there.
Yeah, definitely. So there should be a Schwartzian, but there may be additional. I actually think that there are no additional light modes. I think they are, because they have to do with non-singlet part of the spectrum. And one thing that you can see is that the non-singlets are separated by 1 over n from singlets. So you see this. So what you expect is that there is this sort of absolute ground state and exponentially small gaps. And then this is, for example, the leading non-singlet. So this is singlet. And then there will be 1 over n gap here. And this is n of this n, not n SYK. Will be n of this tensor model. And then again, there will be some, I think, densely. But
I'm going to talk about exactly the structure in complex SYK.
Uh-huh.
There's a U1.
Right.
And you get
Yeah, yeah, it's a different global symmetry, but.
you get exactly the structure.
Mm-hmm.
Not published yet.
Yeah, this we like. There is some effective sigma model argument for why it's 1 over n.
You can also see it's very explicitly in these reduced symmetry models that
Mhm.
otherwise known
Mhm, mhm.
where you reduce O n as a
Right.
whatever to
O n over 2 cross O.
as many of those.
Yeah, there are different sectors here. But somehow they, in the absolute, if you don't add any chemical potentials, I think the singlet dominates the really low energy dynamic. So I just wanted to also mention like comparison between this model and the tensor model. Because so in this model you basically take random A's, right? And now what do you do in the tensor model? It looks very similar, right? You just have a whole bunch of Majoranas. They have these labels. So you basically replace this I by this composite index A, B, C, right? And then you replace J's by a bunch of delta functions. So let me even. So in the fermionic case, you have to do some antisymmetrization. So suddenly, instead of sampling these couplings from a Gaussian distribution, you just replace them by zeros or ones. And it turns out that almost all of them are zeros, actually. So if you write down this, so in this tensor quantum mechanics, this tensor A, I1, I4 looks like this basically: delta A1, A2, delta A3, A4, delta B1, B3, delta B2, B4, delta C1, C4, delta C2, C3, and then plus 23 sign permutations. Because if you want to write it in a symmetric way, you basically include all these sign permutations. And then you can actually compute. So obviously, they're either zeros or ones up to some overall scale. So it seems like rather different. And then you can compute how many are zeros and how many are non-zero by just looking at 1 over 4 factorial of sum of these A, I1, I4 squared. And what you get is the exact answer is 1/4 n cubed n minus 1 squared times n plus 2. And then you see that this basically, at large n, this just scales like n to the 6 over 4. Right? But in the corresponding SYK model, the sum will scale like n to the 12 over 24, right? Because this is just, so this is in tensor, and in the SYK you will get basically n cubed choose 4, right? This number of so it's all to all, right? And then you get something that scales like n to the 12 over 24.
May I ask a stupid question?
Mm-hmm. Yeah.
I mean, basically the one thing is to make a Gaussian distribution of that,
Mm-hmm.
pick a sample,
Right.
right? But then in order to put self-averaging, I believe you have to pick a sample which has a non-zero probability over this distribution, right?
Uh-huh.
And you are picking a sample which might have a zero probability.
Yeah, I think from the point of view of SYK, it's incredibly fine-tuned and has zero probability because.
Then you don't expect self-averaging.
Yeah, but somehow the model works differently. Like, yeah,
Or maybe you don't want self-averaging.
yeah, I think this model is not random, right? This model is
This model is not.
Yeah, I think somehow the ON cube symmetry restricts almost all couplings to be zero. That's basically what we're working with. So it's very mysterious. Nevertheless, it still gives the same leading large n limit, provided you scale things in appropriate way. And that's
But they're different, like in the so-called conformal sector or whatever, right? Like it's just the degree on the Schwarzian part, right?
these scaling dimensions are the same in the leading large n limit. Yeah, because of this, they somehow both of them.
Sigma model moduli ON symmetry, that's about it.
Mhm. But I think that sigma model largely buys you some information about non-singlets. I think in the singlet sector, I would guess the same G sigma action will work. But yeah, it hasn't been fully.
There's no derivation of that, so?
We're
No,
ki-
because if it worked like that, you would not expect 1 over n correction.
Mhm, mhm.
You have 1 over n cubed correction.
It's just it's a more complicated model, but it manages to buy you a very similar set of large n observables. Yeah, and in practice, so you see that there is, so this is much sparser. It's not all-to-all coupling, for example. And
Somehow typical enough.
apparently, yeah. I think it's interesting that even a model with so few couplings still manages to kind of presumably give quantum K. I mean, the argument is that there is the same saturation of quantum chaos in the tensor model as in the SYK model. Right. So this sparseness is what helped us solve the model. For example, even for n equal 4, because the system with 32 qubits is very complicated. But you have to act with the Hamiltonian repeatedly, and the Hamiltonian is obviously much more sparse. It's infinitely more sparse in the large n limit than. Okay, so that's basically the setup. And now, so in terms of the correlation functions, let me just write down a couple of facts. Yeah, I'm almost out of time, right? Who is keeping time? Yeah, 5 minutes. Yeah, so it's just to demonstrate how this melonic resummation works, you so just the UV model, the non-interacting model, will just have so the UV model, right, with action psi dt psi, right? Then you know exactly what the time-ordered propagator is like. So time-ordered of psi ABC of t with psi a prime b prime c prime of 0. Right, that's just going to be product of delta functions a prime b prime c c prime, and you just get 1/2 sine of t. Right, it basically is just a trivial solution that gives you the derivative of this gives you the delta function. And then when you look at the green function in the fully interacting model, basically the interaction gets strong and flows to infinity in some sense. And then this blob, right, is equal to sum of the melonic diagrams, right? Like there is plus this, plus this, and so on. And then you basically replace this by some function g of t. So this becomes some g of t, which in the formal scaling limit will fall off as a power law, right? So one thing is that this g of t again will be equal to minus g of minus t. So just like the sign, it's an odd function. That just follows from the Fermi statistics. And then this Schwinger-Dyson equation is literally exactly the same as in the Majorana SYK model. So you get basically g of t1 minus t2 is equal to g0 of t1 minus t2 plus g squared n cubed. And then here you have double integral dt prime g0 of t1 minus t, g of t minus t prime, and then cube, and then g of t prime minus t. I think actually a very quick way to see how this Schwinger-Dyson equation works is something Subir already showed. You basically want to look at the sigma. Basically, you want to look at the sigma rather than g, and sigma basically is equal to just the product of three dressed propagators. So you get this equation like sigma is integral g cubed. And then you look for a solution where sigma at low momenta, so the full propagator, right, g is equal to 1 over I omega plus sigma of omega. And you want to make sure that at low momenta the sigma dominates and has lower power, like omega to the 1/2 instead of omega for this Q equal 4 model. And then essentially you get the following solution that that this g just becomes minus 1 over 4 pi squared g squared n cubed to the power 1/4. There will be again sine of t1 minus t2, and just power law scaling t1 minus t2 to the power 1/2. And you see that, so here instead of this random coupling variance, you just get this g squared n cubed appearing. Right, and this is sort of in this infrared limit. So this is the IR solution. And it corresponds to this delta psi being 1/4. Okay. So here we didn't have to work hard at all. We basically just looked up the papers on SYK model, and because the equations are literally the same, you find the same solution, except parameters change slightly, like you just have this. And then you can play a similar game for bilinear operators. Yeah, maybe I'll just start next time with that, and I'll pause for questions.
What happens? Can you do this in higher dimensions?
Right. So of course, for Majoranas, like d equals 0, d equal 1 is very nice because there is no Lorentz indices. I think if you do it in one dimension, actually, Micha Berkuz did it for the SYK type model, and then you find that exactly in d equal 1, not surprisingly, the psi to the 4 interaction actually picks up a beta function. So you don't get marginality in d equals 0. Basically, this is a relevant interaction of dimension 0 in the UV, and then it flows you to an interacting nearly conformal theory. This apparently does not happen in d equal 1. Then if you go, one spatial dimension. But if you are above that, then of course psi to the 4 is not renormalizable, so you have to worry about how to deal with that. And now for models of scalar fields, I'll talk about this next time. You can just try to write down, for example, a 5-4 field theory with tetrahedron type interaction, and again formally solve it using bosonic Schwinger-Dyson equations, which work very similarly. And there is some amount of success, like for some versions of scalar field theories. So at least if you're willing to accept theories that, say, live in 3 minus epsilon dimensions. Well, 4 minus epsilon we can do for 5-4, but that model, which one? This one? Maybe 2 minus epsilon, right? Yeah, this one you can do 2 minus epsilon, and this actually is probably an interesting thing to do. But that model probably is just like if you increase epsilon, it will go over to one of the known quantum mechanical models, maybe one of the Gross-Rosenhaus models with more flavors and things like that. But that actually would be an interesting exercise to just sort of do it in a more field theoretic way, like start with 2 minus epsilon, and then similar things can be done for scalar theories. But still, I would say I think the physics-wise the most so far worked out and promising example is the quantum mechanical one, because we already have a lot of known facts about SYK model, and there is a sharp question: how many of them can be reproduced in this tensor model without randomness, and how do they differ? I think it's by no means a fully settled question. And in particular, one of the huge differences is that in the ON cube model, there is a very sharp picture of what operators you're allowed to write down, just all the ON cube invariant ones. And I think I'll break down and show some slides next time, because it's hard to draw these multi-field operators.
So in the graph you show the blue lines, in principle if there are multiple blue lines, they can link to another meaning, or
They can what?
blue lines, you can go in this way or link. Does it have any meaning?
No, I don't think so. I think the only question is, how do they look planar at the vertex, or do they look non-planar, basically? Like some graphs can be obtained, some patterns of blue lines can be obtained from tetrahedral vertex, and other patterns from the pillow vertex. And so I don't think it's like knots. It's just like. Mm-hmm. Mm-hmm. Right. I see. Yeah, I haven't thought about that, but yeah. I think it's just counting powers of n regardless of topology. I think. I mean, I can always draw them as not linked, right? But
These don't live in 3 dimensions.
yeah, they're just drawn like on a. Mm-hmm.
The low energy modes of SYK and this model are almost the same. Then is there a dual for only this low energy sector of this model?
Well, I think it has this. So this operator here for n equals 0. So let's think about n equals 0 operator. This is just basically the Hamiltonian, right? Psi to the 4 by equation of motion. This again has this h equal to special dimension. So this you expect to have exactly the same dual JT gravity or something. But this is just like one mode. And I think in the tensor model you clearly have to couple it to a vast number of massive bulk fields, which even way more than these. This is just a small subset of fields in the tensor model. In the SYK model, I don't think more fields than these have been studied, but in the tensor model, this is a tiny subset. This is like roughly one Reggie trajectory, but in the tensor model, you have like huge number of additional.
These are hard modes, right? In the sense I'm saying that.
Yeah, they're all massive. But if you want to look for their true bulk dual, you have to. They're not like highly massive, right? They're. So I think the only truly soft mode is this one. Still like in the SYK. Yeah, there is a complex version of the model, and I'll probably mention it briefly next time. But roughly speaking, you just put psi bar, like you put 2 bars here and 2 psis, and this model has somewhat different symmetry structure. So this complex tensor, that has SUN cross ON cross SUN squared cross ON cross U1. And U1 is just the overall phase rotation. So I think this is the counterpart. So this is tensor, a counterpart of this complex SYK model that Subir was talking about. And this one also has these even and odd sectors. So basically, in addition to this special operator, there is also this psi bar ABC, psi ABC mode, which is also protected and has H equal 1. And that that's sort of a nice check from. So this has a richer set of operators, right? Like it has now psi bar. So now you can have any integer here. So for even integers, you get symmetric sector. For odd integers. So this one is rather similar to complex SYK. And this has been studied less. I mean, this has, for numerical study, this has even more modes, like 2 to the n cubed instead of 2 to the n cubed over 2. So one has to work even harder to. So far, people have not looked at it too much. I think so, because this model also, like all these models, it has the H equal 2 mode. Like that somehow there is always this subsector, basic subsector. And also in David's models, there is always this H equal 2 mode. And that's responsible for this maximal chaos. All right, thank you.